Hello, this is Mark Unkefer, Director of the Fiber Optic Sensing Association, and welcome to our September webinar. The Internet of Things just got a whole lot bigger. And we're very pleased to be able to kick off this season of webinars with one from Fotech Solutions. And our presenter today is Stuart Large. He's a Sales and Product Line Director at Fotech. And Stuart combines technical, commercial, managerial experience that he's had over 16 years in the oil and gas industry, working at some small engineering firms and some large multinationals. And he's been with Fotech now for a number of years. But what we're going to hear today is really one of the exciting applications of fiber optic sensing in a whole new realm. Stuart, we look forward to hearing from you. Thank you.
Thank you very much, Mark. And good evening from the UK to everybody listening. Thank you for giving up this time to listen to this webinar. There will be just some slight delays as we transition between some of the slides and the video displays, just because of the limitations of the platform we're using, and also understanding there are some delays in transmitting the screens to wherever you might be watching. So please do bear with us for that. So Fotech. Fotech was born in 2007 out of Surrey University here in the UK, to develop distributed acoustic sensor technology and solutions intended for the energy, security and transport markets. We combine talent from across the globe. We are a truly multinational company with a great variety in our workforce. And we combine leading edge industrial photonic and software solutions and expertise in handling that data to provide solutions to a broad range of industries. So we're actually protecting already many assets worldwide. And we have literally thousands of kilometers that are monitored. This covers pipelines, perimeters, international borders, as well as things like cables, both electrical and communications, and a number of other assets. We've got an accumulation of more than 5 million hours for which our DAS systems have been operating in the field, and installations in more than 20 countries. But it's not just about the DAS sensor, it's also about the software and the solution that we can provide. We've invested more than 200 man-years in software, developing a platform which allows us to handle big data, and indeed DAS does produce big data, literally terabytes an hour, but we can't be giving that to our client. We employ artificial intelligence technology so as to handle that data and deliver the solutions that the client requires. So Internet of Things, and following the title of this webinar, well, actually this was a vision that was born for Fotech really near the inception of the company. We were partnered with British Telecom, and we recognized the potential to deploy DAS sensing on the existing communications infrastructure. And as we look today in 2018, we see fiber networks which consist of millions of kilometers of fiber, which we can turn into billions of sensors, essentially. So these sensors are already there in the ground, waiting for us to tap into. But we also need or embrace the Internet of Things. Perhaps a more recent development. It's not something that existed in 2008 when we were born. There was no cloud, and there was no serious big data capability or artificial intelligence. But the benefit of the Internet of Things as it develops is that it allows us to combine multiple sensors, so potentially DAS alongside other sensors that monitor activities in a city. Let's consider cloud computing. for a minute, another important aspect of what we're looking to achieve. In 1996, Netscape predicted that software will move to the web and that cloud computing applications would become common. And obviously this is something we see now. But in 2006, really, Amazon and Google were just starting to market this sort of idea. And they described the paradigm of accessing software over the web instead of a program on your desktop, which is what most of us would have started out with. In fact, it was in 2012 when the term cloud computing was added to the Oxford English Dictionary. As we look now in 2018, we see a range of powerful organizations bringing big applications to the market. Amazon Web Services, Microsoft Azure, GE Predix, Siemens MindSphere, and others such as IBM, for example. And so we're able to harness these platforms in order to build our solution to handle the data from the DAS and turn that data, employ techniques such as machine learning, and turn it into knowledge upon which we can base decisions that may influence what occurs in a city. And so what I'd like to do is start with a video that we've made with our partners, which explains the concepts for how DAS can be used in a smart city.
Imagine a world where cities are smart. A world where your fiber optic communication networks exceed their potential to become powerful sensors, delivering limitless information about the world around them. With Fotech's distributed acoustic sensing technology, that world is now. Installed in control centers, Fotech's Helios DAS technology connects to the fibers on your existing network to send tens of thousands of pulses of laser light per second into each fiber cable. As sound and vibrations arrive at the fibers, our world-leading photonic technology provides invaluable knowledge of the activities occurring across the fiber network in real time. Using advanced artificial intelligence techniques, Fotech's DAS technology monitors subsea cables to detect and locate accidental damage or tampering events as they happen. As the cables run into the city, the vibration environment around the cables provides a wealth of information to make cities safer, more efficient, and smarter. Vibrations created by the vehicles allow you to monitor traffic flows throughout the city in real time. Potholes and subsurface damage create noise signatures that can be used to inform maintenance plans. Detect footsteps and crowd movement. Be alert to pedestrians in secure or critical areas. Monitor mass transit systems with accurate speed and location to better inform public transport. Fotech's Helios DAS technology is already used to monitor thousands of kilometers of secure perimeters around the world, alerting users to intrusion, climbing, fence cutting, and enabling connected security systems to better react. Vibrations occur around fiber cables all the time. Monitor the vibration signatures of fixed infrastructure. Be alerted to deterioration, which can inform maintenance plans. Monitor movements in tunnels, both traffic, large vehicles, and pedestrians. Subsurface fiber cables running alongside pipelines and HV cables can accurately locate leaks and hear the disturbance of cable breakdown to within a couple of meters. Targeted maintenance activity can be fast and efficient. High-speed, real-time analytics pulls all of this information together to inform traffic information systems, highlight efficient routes, and redirect traffic around roadworks Applying Helios DAS technology and advanced AI techniques to your city's existing fiber networks will provide rich data sets, which can be monetized in so many ways. Fotech's experts in Canada and the UK are leading the way in smart city deployments for distributed acoustic sensing. Photonics, machine learning, and AI come together in a way that has never been seen before. The potential is limitless. With Fotech's Helios DAS, the Internet of Things just got a whole lot bigger.
Okay, so in 2016, there was a global fiber optics market estimated at just over $3 billion. In 2021, this is forecast to be greater than $5 billion. Fiber is being buried at an extraordinary rate. The picture here was actually taken by our CEO on one of his recent trips in Copenhagen. Copenhagen wishes to be the first carbon neutral city by 2025. So in smart cities, really fiber is being installed as the connector between the sensors. It's a way to communicate the data that is collected, but also it communicates and connects everything in that city. But we also can consider the fiber now as a sensor in its own right, and that's what really holds the key for us. In 2012, out of the University of Pretoria, Professor Hank de Cavallo e Silva and Hank Jr. Did some work and research into what comprises a smart city. What are the components? Well, we see here smart infrastructures, smart transportation, services, healthcare, buildings, electricity and water distribution, and surveillance. Well, if we look at the role that distributed fiber sensors can partake in this new smart city, we can contribute well to 6 out of those 7 different aspects of the smart city. So Fotech has been working on projects in Calgary. CFAS, which stands for City Fibre as a Sensor, is led up by Professor Robert Ferguson out of the University of Calgary. We embarked on this in 2016. And we're looking at how we can use these systems using dark fibre that's already existent in the city without necessarily installing more from the beginning to measure the activity at street level with high accuracy. So to get this project started, we first of all chose a section of fibre that runs alongside what's referred to as the C train, or kind of tram in Calgary, and is also running alongside a road. And we really connected into this initially just to see what we would see. So I'm going to show you another video now. And this time you're going to see some of the real DAS data, and it will play straight away. So I'd like to draw your attention in the first few seconds of the video. If you look at the the dash cam from the car, you're going to see one of the C trains passing in the opposite direction. The car is being driven a little bit outside of the lane, just in order that it's closer to the fibre, purely to make it stand out above the other cars that are travelling along this road. So I've highlighted for you there where the Fotech car is starting in this video, and then the C train is that thicker band travelling the other way. So of course the C train is a longer vehicle and generates more noise than the car as it travels along. So let's play the video and look at what we see. So looking in the dash cam there, you're going to see the train on the left hand side. Here it comes now, going past us. And then looking at the data field itself, you can see the point where the car that we're traveling in and the C train have just crossed over. And I should explain that on the horizontal axis we've got distance, and on the vertical axis we've got time. Therefore, the angle of the signature of each vehicle is proportional to its velocity. And because distance is on the horizontal scale, lines that are actually shallower in gradient are vehicles that are traveling faster. So as you might expect, the cars are traveling similar or at times just a bit faster than the C train. There's also a couple of instances where the signatures of the C train are slow. You see them slow down, stop, and actually disappear for a short while. These are the places where the C train arrives in a station, pauses for a few seconds to drop people off and pick them up, and then resumes its journey, accelerating back up to speed. Some of the vertical signatures that don't move are overhead crossings, other roads, and we've got cars repeatedly travelling over that intersection. That's also being detected by the fibre. Okay, the next video I'm going to show you is a little, well, it's very obvious, I think. We're going to see a pile driver, which was detected from a fibre that was near a road. The pile driver, of course, puts a huge amount of energy in the ground. It's repetitive, and you're going to see a V-shaped pattern, the centre of which points to the area of the fibre that's closest to the pile driver. But then the sound will be distributed further away on each side along the fibre. Now, this is a pile driver, very obvious to see, but it could equally be a JCB digging in the road, or a pneumatic drill, perhaps from another utility company, or even somebody with ill intent doing damage. And it gives the city or other utilities opportunities to detect this activity, and then perhaps send out a team to investigate and prevent damage being done to their assets, or consider traffic flow. So I'm going to show you this video now. Okay, so I think you get the idea. So let's move on now to what we're doing currently. And this is a live project now, continuation of the CFAS project, but now turning to autonomous vehicles, AV, which are being tracked with DAS technology. So this is a project in which we are one of a few technologies that are involved. There's GPS, and of course there's cameras watching the vehicle along its journey. And so part of the project here is to compare these different sensors and what they can bring in tracking the autonomous vehicle and making it safe to people around it. We're looking at monitoring pedestrians and cyclists and seeing how they might interact with that autonomous vehicle. There's also work going on with experimental fibers, which could perhaps give us greater sensitivity or perhaps extend our range. The range is pretty good, by the way. We usually are looking at a 40-kilometer stretch of fiber in each direction away from the DAS interrogator, but with special fibers this could be extended. Now, the autonomous vehicle is electric powered, and it travels at a low speed at the moment, at least during the trials, 12 kilometers an hour. And the purpose of it is to Calgary Zoo link between the zoo itself and the station and the car park to save guests quite a lengthy walk or travel in a less environmentally friendly vehicle. An open day was held, and the vehicle is affectionately known as ELA, which stands for Electric Autonomous Vehicle. It carries about up to 12 passengers, and for those perhaps from the UK, it's similar but larger than something like the Heathrow pod. And it travels along a road that has been built for it. And so an open day was held to launch this to the media and members of the public, and we got some great feedback. People are very excited to see this technology and to see what's being created here. So I've got one last video for you then to look at this. So we've got actually three visuals here. We've got, first of all, we're showing you a view from just a regular car that's driving the same road. So we've got a view from the dash cam on the right hand side. In the middle we've got the DAS data showing a very bright signature of exactly the location of that vehicle, distance being horizontal and time being on the vertical, hence why the image scrolls down. And on the left hand side we've got a view from our Panoptes server, which is showing you how the fiber is calibrated in space so that we can present the position of the vehicle on a Google map. And there's a very small icon you can see tracking along the image. And indeed, we've just turned a corner, so you can see everything is synchronized. We now cut to a view of the autonomous vehicle as seen on a camera and also in the DAS sound field. The other signature just disappearing out the bottom of that image was a regular car that drove along the same path just a bit earlier and at a higher speed. So the camera is now going to track round to follow the vehicle, and at the moment that was done manually, but there's nothing to prevent in the future integrating the signature from the DAS that tells you where the vehicle is with the camera system so that the camera could be automatically turned to follow the vehicle. It's just now going to go around the corner, and once it gets around the corner it actually slows down and then stops, and so you'll see a curve in the DAS signature as the vehicle decelerates, and then it will go quiet because it actually stops. And of course it's an electric vehicle, so it is actually silent when it comes to a rest. So there we are. Okay, so to conclude, I hope you've enjoyed the videos we've been able to show you here and the work we've been doing. This is the Smart City offering, which is a part of the Fotech portfolio. Most of what I showed you here involves vehicle movement, but actually the Smart City draws upon techniques that we've developed in other sectors. So pipeline monitoring, of course, pipelines run through the city. They could just leak, or they could be impacted by a digger, or could suffer an attempt at theft or sabotage, in which case DAS is a technology to detect that activity and give rapid warning. Cables, likewise, also run into the city and can be hit by digging activities from other utilities, and that can be a very expensive occurrence when that happens. Of course, there is security, both security around perimeters, but also security of the cables and the pipelines themselves, as I've mentioned. And then, of course, there's the road and the rail aspects that all come into this. And so, thank you very much for your time to listen. And at this point, I would like to welcome any questions.
Thank you very much, Stuart. This is Mark Unkefer again, and I just wanted to kind of provide a little note for those people who were calling in as opposed to listening on phone. You wouldn't be able to hear the sound from the video, which I probably should have mentioned at the outset, but you will of course be able to listen to that when we finish recording it and post it on the website. Stuart, could you kind of provide a little context? Obviously, there are a variety of different technologies that are available for smart cities. So, for example, with what are the advantages to DAS for traffic monitoring as compared with GPS?
Yes, good question. In fact, I believe at the Open Day in Calgary, that was one of the questions that was asked. And so our answer to that is that all technologies have their benefits and perhaps some of their limitations. And the GPS suffers a few things, particularly in the city. You have the issues of the communication to the satellites bouncing off of the tall buildings, and therefore actually sometimes throwing the GPS off target. It can be impeded by severe fog or perhaps smog, unfortunately, in some cities. And of course, it definitely won't work underground in a tunnel. Whereas DAS is a sensor that is at ground level, so it can run through a tunnel right next to the road, or along. It's unaffected by the weather, and so it really helps mitigate those issues. You also have, of course, the late adopters, those people, perhaps like me, that like to drive an older car, and actually, we won't be buying a car that has a GPS on it anytime soon. Well, the DAS is not really concerned with what particular type of car you have. We still see your signature as you drive along a piece of road. And likewise, things like Google Maps, that uses mobile phones to identify traffic. And in fairness, it's very good at recognizing where traffic is moving slowly and detecting a queue in the traffic and predicting your journey time. But it doesn't track all of the vehicles. It's actually quite a relatively small percentage that have, at least in the UK, a Vodafone phone, I believe it is, that gives the data to Google, and so they can't actually detect the flow of traffic, exactly how many cars are traveling through a particular point in the network. So we all have our strengths and weaknesses.
That's helpful. In the Calgary bus project that you described, could you talk a little bit about how the acoustic fiber or the fiber optics is integrated? Does it help guide the bus? Does it track it? How does it tie in?
Well, at this stage, it's sort of an experimental stage where we're determining exactly what role DAS or the other technologies have to play and how they might interact together. Clearly, we can track the position of the UAV or the AV very accurately, but then we also need to be looking at monitoring the position or impedance of pedestrians or cyclists that could get in front of the AV and cause it to need to stop. And also, that is sort of really the next step here, is to take what is clearly very rich data in terms of identifying things happening near the fiber, but to actually then turn that into the right kind of data, or if you like, knowledge, that can be fed into the actual control systems. For example, in a city environment, the traffic lights at an intersection so as to perhaps make a live, real-time decision that says, well, leave the light green for longer to let this vehicle come through that we've identified. So that's what we're working on now.
Next question is how deep and how is the optical fiber buried in the ground? And I might add to that is can fiber that's already there be used, sort of reused for this application?
Yes. So the fibers, the whole idea of this concept is to use the fibers that are already in place. If we don't have to put in more sensors, then all the better. We save a lot of interruption and unnecessary roadworks, etc., as well as cost. So in the very first example I showed you alongside the road and the C train was just fiber that's been there probably for a few years already. And hence there are some spots where we've got real brightness in its signature, great sensitivity, and some areas where it's not so good. But that's okay because there's still enough wealth in that data that we can make something of it, and it's still a lot better than a series of point sensors. However, what's also encouraging is that the techniques for installing new fiber cable, perhaps alongside a road, are much improved and developing quickly. I've seen systems that can create a micro trench, say 6 inches deep and ½ inch wide, and it requires 1 or 2 people to walk the machine along the road and then backfill the trench with the cable inside, and they can cover a few kilometers a day doing that, and it's really quite a cheap installation. So if we deem that there are areas of road where we need to put in new fiber cable because we haven't got something that's already good enough, then it's not such a big deal. In the case of the autonomous vehicle, well, then that was a special installation because it's a purpose-built stretch of road, and they were thinking about deploying DAS at the time of the installation, so they did it exactly how we would like alongside the road. And I think that's the thing going forward as people become aware of this capability. If you're installing a new fiber cable, let's put it in a place where DAS technology can be deployed rather than just perhaps throw it in a conduit or a trench, just how you might have done in the past when it was solely for communications.
That's good. And we probably should make the point at this interval that when we're talking about DAS in this context, we're talking about distributed acoustical sensing. Sometimes in the smart cities, it's DAS means distributed antenna systems, which is a somewhat related technology, at least in the smart city space, but really is a completely different altogether. Next question, I guess, is a question about the videos itself, and is the sound that we were hearing extracted from the DAS data, or was it recorded separately using a microphone?
Oh, those sounds were from the video cameras that were watching the pile driver or the dash cam in the car. However, we do have technology, advanced processor that we call EDAM, which allows us to capture specific areas of interest in the data. So if, for example, we detect digging and the algorithms highlight that to us as an alarm, then we can start recording that small section of fiber. So it might be a 50-meter stretch of fiber, and we'll also go back in time a little bit because we've got a rolling memory. So we'll start recording from a few minutes before the alarm, all through the period of the alarm, and then a few minutes afterwards. And then we can keep that area of interest, and it's raw data, raw DAS data, which is useful then for us to feed into future learning. We could put that into our machine learning platform, and we can use that to develop better algorithms, better detection techniques in the future and improve that sensor. But we can also turn that into an acoustic audio file so that you could sit at your computer, put headphones on and listen to it.
Next question is, what is the maximum distance that the sensor can sense? And I guess there really are two parts to that. One is the length of the cable itself, but also maybe from the cable to some nearby point.
Sure. Okay, so the length of the cable, that really depends on the quality of the fiber and the environment around it. But typically, we say 40 kilometers, and that's because we'll see an optical loss of up to about 10 decibels. On some fibers, it might be as bad as sort of 12.5 dB. But then we can, in certain applications, we can extend that to 50 kilometers or slightly more. We have a couple of installations that are limited in detection capabilities, but can extend the range out beyond 50 kilometers. We can then have two channels on a system. So, for example, on a pipeline, we can look up the pipeline and down the pipeline from one point. Or obviously in a city, it could just be a couple of fibers that go in completely different directions from each other. So that's length. For distance away from the fiber, well, that depends on a few factors. There is how that fiber cable, actually the construction of the cable. Do we have good acoustic coupling from the fiber in the middle of the cable to the outside wall? Which is why we're always interested to talk to the manufacturers about how they construct their cables. And then there's how the cable is laid in the ground itself. Is it directly buried in a conduit or in, say, sort of a trench, and how the ground is around it, if it's suitably compacted. And then, of course, you've got what is the source itself. So typically, if you're, I say it depends on all those factors, but as generally walking, you're going to detect that at sort of 5 meters each side of the fiber cable, but sometimes it can be as much as 10. If you're looking at digging, digging with a spade, a person with a spade, maybe 10 meters or so. But then something like excavation with a JCB can become 20, 25 meters. And then something like that pile driver, we were seeing that from a few hundred meters away. So yes, it depends very much on a number of factors, but that gives you a sense.
Sure. Does the process of the DAS, the analysis of the DAS signal coming from the fiber, does that interfere with the communications that also may be going through that fiber optic cable?
No, not at all. Of course, the cable could have many fibers inside it. In fact, in the city, most of them will have potentially hundreds of fibers inside. But we'll be using a fiber that was originally dark. It's not, so our fiber that we're sensing with is not used for any communication. It is purely for the sensing. But that one fiber that we're sensing with will not interfere with any of the other fibers that are in the same cable.
Sure. And it seems that telecom companies could use acoustical sensing over their existing networks to collect information that might be of value to the cities, road conditions, traffic, other things. Has there been much discussion about how there might be some revenue sources from this for telecom companies, a way of monetizing this information?
Yes. There's a number of discussions taking place. Obviously, I can't reveal with whom and to what extent, but certainly, they can protect their own assets, protect their own cable to make sure it doesn't get broken by being perhaps dug through or prevent it from being tampered with. But it also gives them opportunity. Should something be occurring around the cable, if they want to take a preventative measure, they could divert data communications via another route until that threat is resolved and passes away. But also, of course, you're right, they can effectively sell, acquire and sell that information to other interested parties.
That's good. I think we've reached the end of the questions so far, so I will thank you, Stuart, for a very informative presentation. I'll also mention that we have a couple of webinars coming up in October. We'll have on October 18th a webinar with Oz Optics on fiber optic sensing. And then in November, we will be doing a joint webinar with CFOM, some of the work that they've done on downstream applications. So both of those are things that can be registered online. Just to answer a question that frequently comes up, we will be posting this webinar, also the video in particular, the videos, I should say, plural, will be available on our website and also on the FOSA YouTube page. And so you'll be able to download that and listen to that in the future. Stuart, thank you very much. Very much enjoyed this presentation.
That's good, and thank you, Mark, and Joy as well for your efforts in putting this together. I've enjoyed it, and appreciate it.
And that concludes.
Thank you.